Hello, welcome to another episode of Beam There, Done That. Again, I'm with my so-so co-host, Francesco Cesarini.
Hi, I'm Francesco, so co-host today. Welcome everyone. So this is our third episode on the right tool for the job. After Rust and Elixir and Zig and Elixir, today we're expanding this question a little bit. Not which native language, but how do you actually go in and choose a stack at all for a system which is under real and extreme load? And the system we're talking about is a piece of blue sky, so the whole data plane. And the data plane is the part that turns a fire hose of events into the timeline you actually read on your phones. So the open reference version handles a few 100,000 users. Blue Sky's own one runs at millions, but it's closed and solved with brute force, running very, very close to the bare metal, to the hardware. And that's that gap in between what's stopping other platforms from growing. That's the gap. And today on the show, we have an old friend, Chris Beck, who, together with his teams, set out to close it. And here's the twist: they work with Go, Rust, Node, and Elixir every day, and they weren't expecting to achieve, the speed with Elixir, and instead, believed, it would happen with Go, Rust, possibly even Node. But when they started, stress testing the proof of concepts, the workload they were stress testing everything with sent them somewhere they didn't expect. So, Chris Beck of Bitcrowd in Berlin, welcome to the show. Why don't you tell us who you are and how you ended up building a piece of blue sky?
I'm Chris. I founded Bitcrowd 16 years ago. We just celebrated our birthday in May together with a friend. Now we are 10 developers and we are solving problems for companies like the Deutsche Bahn or the Lufthansa or the Charité. So mainly systems that need to scale and that need to stay online and need to be reliable. And also we do open source in that we believe change the world to a better place. That's maybe how this whole project started.
Nobody asked you to build a piece of blue sky. There's a perfectly good reference implementation, and your Blue Sky's own production version exists. What made you look at this missing component and decide it was worth your team's time? And was there a point where, in this process where you actually regretted starting, to look into this?
Well, actually, I'm like, there are no regrets. Like, I'm totally thrilled. Many people don't know that Blue Sky is not just another hyperscaling application, but it's actually built on top of a protocol that's called Authenticated Transfer Protocol that you can think of as an operating system for social apps. So if you build on that, you instantly have all the follower graphs, and there are thousands of applications built on that already. Like you have things like photo sharing, or you have things like social coding, just like GitHub. It's all based on this application, this ad proto. And the good thing is when you use that, you don't have to take care of all these social connections and graph. That's all inside this ad protocol. That's quite interesting. And the people from Blue Sky are actually making serious efforts to put that into the open. Like their whole code is open source. And they are also making efforts to get this ad proto recognized as an IETF standard. And that's where they ran into Alistair Whitman from the Erlang Ecosystem Foundation. And he pointed me to it because there are many people in Europe and all over the world that are that are working on using that infrastructure for their own social networks independently from Blue Sky. And they're like struggling at scale or like at potential at scale. And that's what grabbed my attention.
Now, a lot of people don't really work in the social network area, Facebook, etc. I mean, Blue Sky is another type of social network, in my understanding. they have this component called a data plane, right? So, and you've been working on this component. Where does it actually sit in the whole architecture of Blue Sky, and what's it actually used for?
Yeah, if you create a post on your mobile phone, then the first thing it gets transferred to is your personal data store. That's kind of the home base for all your data. It hosts like a content archive with all your likes, all your posts, all your things that you did on the network. And from there, it's picked up by the relay, which looks at all these personal data stores and indexes all the messages to the firehose. The firehose then gets picked up by the personal data store of your reader. And as soon as they open their laptop to have a look at the messages, then that talks to their personal data store, which talks to their app view, and the app view then talks to the data plane. The data plane is the part that indexes all the incoming messages, stores them, and then has the job to compile your timeline. So basically, it's the part, as Francesco already introduced it, that's making the transition from the message bus, which is like the firehose, to an application state that your mobile app can consume.
So we could basically say that it's kind of catching all this raw data stream and turning it into like a timeline view. Like when we go to Facebook, we can see top to bottom latest kinds of things happening in our social scene, right?
Mm-hmm. Exactly.
Put it in numbers for us. What does the system actually have to handle at peak load?
It's very interesting with those social networks that they have often a very modest average load. Like it's at normal times, like at this moment, maybe there are 200 to 500 messages per second. So really boring. But we have like two events that we were able to observe in the past where this skyrocketed. Like one of them was when Brazil banned Twitter, and so then the numbers skyrocketed from there. And the other one was, of course, the US election in November 2024, where the networks saw like 6 million active users, who were checking like their timelines all the time and who are posting all the time. One of those numbers, like how many posts there are, we can observe by just looking at the firehose or like the historic data of the post. The other thing, like how many people were online, how many were checking their timelines, which is like the more severe traffic, we cannot without like having access to the logs of the paid personal data stores. But we like for our studies, we wanted to arrive at a point that can handle loads and that has also headroom for growth. So we were targeting for traffic in the millions and something like 10,000 messages a second.
So, of those two pressures, so the incoming firehose and millions of users checking their timelines, which one actually shapes the design?
At first, we thought that the firehose itself is like the problem, like the amount of data. But then we realized that it's already a perfect caching layer. When a message arrives, it needs to get indexed, like the at proto first checks, like, is it valid? And then stores this into the database. But it can do so in its own time. Like it receives a message and it somehow needs to like, it shouldn't lose that message. But then it can like catch up on its own devices in like its own time. You will not like as a user, you will not call the provider because a post arrived at 11:45 instead of 11:40 or something. So that's a load, but that's a load that can be managed quite well. What is more severe is this load that happens when the user like takes their phone and then wants to see the messages. Like you can display a loading bar for some like seconds or something, but then things need to happen. And because there are millions of users doing that, you don't want that to happen in seconds. You want that to happen in milliseconds.
Now, we recently did an episode with Elise talking about game servers. You have a lot of users, real time constant updates. How is this different from, how is Blue Sky different than, say, actually making a game server?
Yeah, first of all, thank you for that episode. I enjoyed that so much. It's so great to see how, like, what a great knowledge Elise has on that. To your question, when you shoot a bullet in in a multiplayer game, then you need to deliver that event, first of all, in a matter of milliseconds, so there is no lag, and second of all, in the right order. Otherwise, you get shot by a zombie that's already dead. Wait, zombies are always dead, but like the monster that you already killed. So you need to be in time and you need to be in the right order. That's totally different for a social network graph. No one goes there like a librarian or something and goes through all the posts and takes care that they're at the same time. Also, it's all happening at the same time with millions of users. There just messages arrive at the same time. You just need to take care that a message doesn't arrive before its parent. So you don't have this timeliness constraint, and you don't have this constraint for completeness. Like it's different. You cannot drop a bullet in a multiplayer game, but you can really not display a message to a user because they are like when they're scrolling, they will get distracted after like 10 or 20 seconds and read something, go off somewhere, comment or something like that. So even if you have like if you're following like thousands of people, you will never read through thousands of posts once you fire up your timeline. It's you can if you like scroll down to Blue Sky, then you find out that after 2 or 3 days there are no messages anymore because that's the time frame where your timeline has been prepared for you. And while you scroll down, you already see like new messages coming in that divert you from your timeline anyway. So you can just drop messages in the timeline and you don't need to deliver them like in a matter of seconds after they were created.
There's an open reference implementation already. Why does it fall over and what specifically breaks as you grow?
Yeah, first of all, like I think we need to be fair to this reference implementation because it's not meant to be in production. It's more like it shows you what needs to be done in the most simple manner. For instance, it just does a join of feed items that come in over the people you follow to your user account. And that's on terabytes of data. It's totally clear that that is not performant. And it also doesn't feature any of the performance improvements that we know social applications always do, like who gets displayed at what gets displayed at what time and stuff. So it's just more like an outset on how to handle this. I think there's a blog post an interview with the people from Blue Sky where they tell us how they started with an implementation of Node and Postgres, which is probably very much similar to the one that they have that is now the reference implementation. And they discovered that they can only scale with Node by adding more nodes to it, and that they also have a problem with Postgres in requiring like this one main server that you connect to. And so they were only able to scale vertically with the node servers, and they were not able to scale vertically with Postgres. So that was their problem, and that's where they changed their implementation.
It sounds like the way Blue Sky is doing it, their own production version, the way they're solving the problem is something that like smaller teams cannot basically easily copy and use their existing implementation. Is that a good way to say this? Because it sounds quite complicated when I'm listening to you talk about it.
Yeah, I mean, at one point, Blue Sky made a similar move to the people from Discord who first switched from MongoDB to ScyllaDB. They first switched from MongoDB to Cassandra and then to ScyllaDB because it had less problems with garbage collection, and they were able to solve many problems just by having lots of servers from that. The problem is not that it's so much bare metal, it's more like that you need a huge infrastructure setup to run it. So say you're coming out with social network in Europe and suddenly everyone thinks like, okay, this is the new thing, this is where we've got to be. Then suddenly you exceed the capabilities of the reference model and you have nothing to go with until you reach like that point of users where you can afford like large structures. And we wanted to fix that so that communities in Europe and everywhere in the world can basically start to set up their own Blue Sky without being afraid that the whole infrastructure might crash with like when they reach 1,000 users, which is where it gets interesting for those communities.
It sounds like a very much like a read-dominated workload with two very different halves. So you've got the reference version, that treats them as one and draws in joins, and you have a production version, solved with hardware, nobody else has. So, that sets up the real question, not which language is the fastest, but how you let the shape of that workload, choose the stack. And this is where we'd like to spend the rest of our time on this episode. So you've pinned down the shape of the load, and before you looked at a single language, what did that workload actually demand? What was the requirements list the load handed over to you?
The requirements list was to be able to deliver a timeline in a matter of milliseconds, or if push comes to shove, in seconds. And on the other hand, being able to host a whole trove of data in the terabytes. So it was clear that not one like magical database and not one magical operating language would do both. It was clear that we needed some kind of system that would, from components that would fulfill all those things. And we actually, for this work, only looked at the hardest part, like the compilation of the timeline. And that's like where we put our main focus.
You might have focused on the timeline, but you did mention it. The workload has two halves. Can we go into a bit more detail on these two halves? Because I think the whole design decisions turns on them. There's a hot path, there's a cold path. What does each one need? From a runtime.
Yeah, so from the runtime, it just needs to be like very only the recent data, but very fast, and it's more memory and compute bound, and that's like most of the times the dominant request. And there's also like the deferrable back pressure and queue that you need to do, and then there's the code path, which are like records, profiles. Maybe someone reads through a thread that is like 2 years ago, but that is something that is singular. You don't have to look at who wants to see this, who wants to read this. You can just happily ask like your data management system for that. So that's more like on the IO heavy side.
From what I understand, you at least work in 4 different really high performance languages, right? You got Go, you got Rust, you have Node, and you have, of course, Elixir. Can you start to walk us through, you know, basically what are the pros and cons of each to actually solve this problem, in the respective languages? Let's start with Go, right? I mean, of course, it could probably solve the problem, but there has to be a cost. There's no silver bullet. There's no such thing as zero cost, implementations, right? So why did Go not fit this situation?
Yeah, I mean, of course, like Go is the incumbent there. We know that the Blue Sky team went there and solved the issue with their scale. But and like Go has pretty good concurrency and everything. The problem is that you would need to handle your supervision and the back pressure, and and also Go is like notorious for this garbage collection lags where it just doesn't do anything. And that's, of course, something that you can tweak. Like someone who's running that kind of system in a great scale probably knows quite well how to tweak it to the current load. But we figured that that might be a knob that we would like turn forever.
Now, what about Rust? Because Rust is kind of a really good language. I mean, you could take a look at like Discord and so forth. They are a big proponent of using Rust. So how about, again, how about Rust?
Yeah, Rust is great. Like it surely doesn't have a garbage collection to wait for. The thing is, like it gives you a lot of safety and a lot of protection for your business layer, but it also that comes with a cost. Like the development or our development speed is great when we exactly know what we are doing. But if you need to build and rebuild and try out things, we think that Rust is not such an easy partner. You just have to work quite thoroughly and for a code that you maybe tear down the next moment. And it was obvious that like this target would not only include doing it once, but also like trying out things, trying out scheduling, trying out different compilation of timelines. So the biggest disadvantage from Rust in our like view for this project would have been that we would have spent more time on working with like implementing those things in Rust, maybe more than we can have time for a project that's like more or less a side project.
The reference implementation is implemented in Node. What about Node?
Yeah, I mean, Node is notorious for its like single-threaded scheduler loop, and which makes it very hard to scale. And yeah, maybe we only looked at it for completeness because like the Blue Sky team already had abandoned it. And I'm pretty much sure that you can also scale Node if you put time into that. It's just not something that we wanted to do.
In the end, you ended up landing on Elixir and you weren't really expecting it. Why is that?
Yeah, I mean, we didn't expect to land with Elixir because the whole ecosystem is like kind of sold on Node, Rust, and Go. And so even though it's like one of our favorite languages, we kind of treated it with caution. Also, like Beam has just like it has all these great features like back pressure, observability, robustness, supervision, all the things that we would need to rebuild with the other toolings. But it has one weakness that like the raw per core compute, especially like in things like bitmap operations. So when we wanted to compute the follower graph, like pure Elixir itself or like pure Beam languages itself would have had a problem.
It's interesting because at the end of the day, I mean, you look at the Beam, you look at Erlang, you look at the Beam. It was implemented, to switch phone calls, but we quickly discovered, that you went in and you switched instant messages, SMSs, money, stocks, or the way what we discovered back in well 2008 2009, tweets, the business logic was still the same. So it was incredibly, at least for the ingestion of tweets, it was absolutely brilliant. I remember, we were working on a Twitter clone, which was actually connected to Twitter, at the time where it was exporting APIs, and the scale we could reach was on pretty much commodity hardware was really really amazing. it was slightly different. It was slightly different challenge to actually go in and serve the timelines, but again, there we knew that it was mainly, the tweets from, the last day or two, which, the users looked at. So, and that's how we got around to that, caching them in Amnesia. So yeah, it was interesting. Going back now, so you've got four candidates, each had, their flaw, and you said the interesting move wasn't arguing it on paper. It was asking, which flaw could you actually engineer away? So through it, whose flaw is structural, and which flaw was structural, and which flaw were you able to fix?
Yeah, I think here's the thing. You can, when you have your own side project, you can pretty much, you have the privilege to decide which problem you would want to solve. Every one of those languages like run services in scale. So we could have gone with Go and do work on tuning the garbage collector and do work our way into that, or build back pressure there. Or with Node, we could have worked on the event loop to make that a better place. With Rust, we could have built like more developer tooling, and so to make it more performance. And those are completely valid problems, and people would have been like happy for us to take them on. It's just that we thought it might take more time, each of those, than we would have at our hands on a side project. And what kind of made the decision that Elixir already had solved parts of the problem for us before we started. Like Elixir's real weakness, like the raw compute performance, is kind of remedied by its capability to use the cores of a machine very efficiently. So if you have lots of processes and can get around like this, that a process like some operations take a bit longer, then that's already perfect. And like Elixir or like the Erlang ecosystem already had a piece that already solved that for us. And then it's like Erlang term storage. That's a BIF, like it's a key value store that's written in C and is like built-in function. So it's already like doing the thing, or like proposing a path there where it's like using C for a computation. And we could just use that to store our timelines and to store who follows whom and who is followed by whom into ads tables. And they worked already perfectly because it was actually scheduled out to C. And we only added the roaring bitmap in.
That is exactly how we solved it back in 2009. We usually tend to call ETS tables, the Redis of the beam. So yeah, incredibly fast and incredibly efficient.
Yeah, and we only added the roaring bitmap implementation from Rust afterwards because it was obvious that we would need it to solve the social proof feature, where you say like who that I'm following is following like this person as well, and that's like an expensive operation if you do it on scale in Elixir. But there's an implementation like roaring bitmaps that gives you bitmaps that are normally always sparse in their density. So, and gives you quite of a compression on that, which is still performant. So we were able to just pull that in and have like very performant base to solve that.
Erlang historically and today Elixir pretty much lose every single micro benchmark. And you raise this in yourself in your blog post. That's a strange thing to write about the language you choose. How do you pick the thing that loses on paper?
I mean, if you are somewhere where you know that there are dark spots, then the first thing that you ask yourself is, do I need to go there? And for us, we found out that with using this ads implementation and with the Beam being efficient at scale for many clients, that's already that that's already enough so that we don't need to go to the corners where we need like raw compute. So that's why we're able to choose Elixir, though it's like on the micro benchmark, it's losing every time. But it was like losing on micro benchmarks that were not so relevant anymore because we didn't need to know like, is this user following this person? Because we could just ask ads to give us the whole list of followers, and then we didn't need to do like descent into this micro benchmark.
Let's still kind of stick onto this topic right now. The beam itself is not great at, these some kind of hard computing crunching of numbers and things like that. You managed to put that part into a NIF using the great, Rustler library we brought up before. How did you manage to do that, and how is the implementation? Because I believe you have it so that basically that memory, I believe, doesn't even touch the beam's memory. It's kind of staying by itself, if I remember correctly. Can you explain more about, how you managed to kind of separate the two concerns, yet they work together very well?
Yeah, you need to keep them apart. First, we never needed to leave the beam for the simple features. We could just follow that into ads. The beam owns memory storage, and like it lives on its own memory, and it kind of leaves the system, and you need to copy over data when you use that. But we knew that our data is like relatively small, so that was not a performance like gap that we needed to address.
Going back, I did mention about Discord, right? Do you mind to discuss a little bit about what Discord did, and is that basically your the inspiration of doing what you have done with your data plane?
Yeah, Discord kind of does the same. It runs its real-time messaging on Elixir, and when they hit like their weakness on the beam, the hot data structure operation, they dropped that into a single piece of Rust and included that via Rustler. The funny thing is we didn't know about this story, or like we hadn't looked into the story when we worked on that. We only found out later, and it's like good to know that we like arrived at the same conclusion.
Every native boundary has a price. What did the sniff actually cost you?
Yeah, I mean the NIFs run in memory, so a crash can take down the whole virtual machine. So you give up kind of the isolation and let it crash boundary, the let it crash paradigma to exactly at that boundary. As I said, like we had the example of ads as a BIF, and that's an interface that is quite stable and that has been worked on for like maybe decades even. And what we were doing with the NIFs seemed to be kind of the same thing. Like we had a very distinct piece of code where we knew the runtime characteristics quite well, and we also knew that those calls would usually terminate in the matter of nanoseconds, not like seconds or something. So we felt safe to take that risk and to take that cost.
You said that the NIF made Elixir competitive, but the fan out requirement is actually, what you based your choice on. And I'm trying to understand this better. Why is the fan out part, what made you decide on the approach?
Well, because we were able to put when a tweet arrives, we were able to put in a lot of those messages directly into the mailboxes of the users at the moment they arrived. And that feature, like this BIF and NIF, really got Elixir back on the starting line. It was like it removed the reason not to use it. And the spec was like this deferrable queue as well. It would we know that it would apply back pressure, it would absorb burst, and would degrade gracefully. We even had problems with that when we were building our performance tooling, And when we let that run against like the data plane implementation, the reference implementation, the back pressure always behaved so nicely that the node system that we were testing would not crash because it like naturally did back pressure and things. If we had done the same thing in Rust, in Node, or in CAF, in Rust, in Node, or in Go, then we would have ended with like some kind of key value store that's external. It would have added costs to establish the network connection, to receive the results. And it would have been another like potential performance bottleneck on the surface between those two systems. So here in Elixir, we had all those kinds of these things readily available, and we didn't need like a serialization around queue boundary.
It sounds like you had to deal with trade-offs right here. Can you describe them from a high level?
Yeah, I mean durability. If once the client goes down, the whole data is not the client. Once the instance goes down, then all the data is gone as well. But it's something that we can easily recover, especially in a situation where we would run like multiple nodes, which are able to take over at that point of time.
If you had to put this whole decision, we've been talking about in one sentence for someone who has to pick a stack tomorrow, what is it? What is the sentence?
Yeah, ignore what seems obvious. Start with a shopping list, and the boxes to tick off, and ignore that one of the problems is maybe best used by framework architecture A, B, or C, and instead have a look like what cannot be solved and which of the problems you like to remedy.
You've basically proven the hard part that Elixir can mostly handle this. For the bits and pieces that it cannot, you can use a NIF with Rust. What's actually left, right? Because you have basically a working proof of concept. What's something that say the platform could say, okay, now we're ready to switch over, and what's kind of left to still do?
Yeah, we started with the hardest part because we wanted to be sure that we can contribute to that. In the app view, after it called like the timeline, it needs to do all kinds of other operations. Like it would then call the data plane again to get like the profile data or to display the post. It might call the other posts that are related and display them as well. So there are a lot of operations. Actually, the interface contains like 96 endpoints. I think around 80 of them are quite trivial. 10 are harder, and 6 are really hard. And we solved like 2 of them already. And now what's left to do is to implement like the easy parts and to find a solution that matches the hard part. On the other side, there is also the indexer, the part that reads the incoming messages, that also like has around 10 plus plugins that you would need to write in order to actually persist the data.
For someone picking a stack tomorrow, what do you want them to take home, from this podcast?
Analyze the workload, try to be as open as possible about the solutions.
Now we're starting to kind of wrap up the episode, so we'd like to let people, if they're interested in, say, something similar, or to actually get in contact with you. What's the best way to keep up with what's going on with what you're working on, and also the other things you're doing at Bitcrowd?
Yeah, there's bitcrowd.dev is our blog post where we report on those things. There you find all the ways to reach out to us, and it like would be great to hear from you, especially if you're building up your social network. Give us a shout. We've built this performance tool which can actually give you input on how performant your system is before you need to test it in production. Yeah, and we would really love to collaborate on this.
We've got 3 episodes now on the theme of the right tool for the job. We started off by looking at Rust. we've looked at Zig, and today, we've got a whole stack which we've picked by production patterns, we've picked by workloads rather than by technology preferences. And every time, we have an episode like this, the honest answer is always the same. Use the beam for what it is brilliant at, and use native code for the one thing it isn't brilliant at. And what Chris highlighted today is that you should base your decisions on facts and choose technology, based on evidence, because at the end of the day, if you're switching phone calls, instant messaging, data packets, money, SMSs, or Blue Sky posts, the logic is still the same. So, Chris, thank you very much for being on the show, and a big thank you to all our listeners. If you're new to this podcast and it's the first time you're here, go back and listen to the Rust and Zig episodes and subscribe. So, and for everyone else, until next time. For the record, this episode was recorded June 15th, 2026.